All right. So we left off last time talking about conversions. If we want to convert the mass of 36 pounds to grams, we need the conversion factor. 1 pound equals 454 grams. And then we can set it up in this fashion, and that will find us our grams. Okay? All right. So continuing talking about the metric system, units in the metric system, these are pretty basic units that we would use in science. Length, you would use the meter. In the English system, it's the yard. The liter, or a quart in the English system, and then seconds. That's pretty standard. Seconds are pretty standard. So these are the units of length, volume, and time that we would use. Okay, and these are the prefixes that we would use within the metric system. Okay, let's see, those are pretty terrible. So let's see, right here. Okay, that's better. Things like mega and kilo and deca and deci. You're probably familiar with mega, kilo, even giga now, gigabytes, right? Terabytes. So that's just an increase by 1,000 every time. So a kilo is 10 to the third. A mega is 10 to the sixth. A giga would be 10 to the ninth. Okay, so you're increasing it by 1,000 each time with those units in the metric system. Now, as we go down, you have kind of the same effect. Not necessarily between deci and centi. That's 10. That's 100. Milli is 1,000 less. So that's why they say 10 to the negative 3. So what people struggle with a lot with these is kind of perceiving what these numbers are representing. So if it says 10 to the negative 3, okay, that's how you relate it to one of the base units. So if the base unit is grams, okay, and you have 1 milligram, then that means you have 1 times 10 to the negative 3 grams equals 1 milligram. Okay? So that's how you would use this number. This would be the conversion factor right here that you can use. Now thinking of it that way often makes people think like they're thinking backwards. So you could do this. You could say 1 gram equals 1 times 10 to the third milligrams, or in other words, 1 gram equals 1,000 milligrams. Okay? So you need a lot of milligrams to make 1 gram, or you need a very tiny amount of grams to make 1 milligram. These two things are exactly the same. They're exactly the same. Okay? But sometimes people are like, wait, when do I do 10 to the negative 3 and when do I do 10 to the third? Because you could do both of those here, right? You could use 10 to the third here or 10 to the negative 3 here. But depending on how you set it up, you're going to have a completely different answer. So make sure you're getting it correct in the correct way. You're understanding how these are relating to one another. Okay? The gram is bigger than a milligram. So the gram either needs to be really small to be a milligram, or you need a lot of milligrams to make a gram. So, but either one of those will give you the exact same answer. You just have to make sure you're using it correctly. Okay? And milli is probably the one that we're going to use the most. So that's the one you need to really be familiar with. Milli and kilo. Okay? We'll use those a lot. So you need to remember how to do those conversions between milli and kilo, because I will not give you a conversion factor for it. Okay, you need to remember there is 1,000 milligrams in a gram, or 1,000 milliliters in a liter. Okay? you need to remember that so that you can set up your conversions correctly. There is 1,000 grams in 1 kilogram. Okay? So this is just kind of representing kind of how it would be. This, if this is a centimeter, 1 centimeter, okay, which is, well, the face is 1 centimeter, okay, the length, I'm sorry. But this has a cubic volume of 1 centimeter cubed, okay? So it's 1 centimeter cubed, which is equal to the volume measurement of 1 milliliter. 1 centimeter cubed and 1 milliliter are exactly the same thing. So if you're going into nursing, you'll probably deal with this a lot because you have to deliver certain amounts of volumes of medicines to your patients, and maybe but not in milliliter amounts, in cubic centimeters. So deliver this many cc's to this patient, right? Cubic centimeters, and that's what they mean, but it just means the same as milliliters, that many milliliters. It's the exact same measurement, okay? Okay, so we get to, so then this would be the measurement of an entire liter of a solution. So volumes are in these cubic measurements. Okay, we don't often look at them in cubic measurements, but that's how you would measure things in volume, is through cubic measurements. Milliliters are in cubic measurements, just through, they relate by centimeters cubed, okay? Whereas the meter would relate to the liter. Meters cubed would be 1 liter. Okay. So now we're going to start talking about significant figures. And we've talked about, if you're taking my lab, we talked about significant figures a little bit already, but now we're going to get into it a little deeper and make sure you guys are understanding these. Okay, so significant figures are the figures that bear the information of a number. They represent the data, okay, and all the precision within the measuring device that you use to collect that data. So if I have these two measuring devices, you can see the first one, if I measure the length of that red line, okay, it would end up somewhere between 5 and 6. Well, I know it's for sure at least 5, so I'm going to say 5 point something. Okay, and then I have to guess what that last digit is. 5 point, and you make a guess. 3, 5.4, 5.5, wherever you think it's hitting. Okay? It's just a guess. And significant digits are always recorded to the last guessed digit. So here, to record the number of significant digits in this measuring device, I would have to record 5.4 or 5.3. Doesn't matter. Either one would work because it's just a guess. I'm just guessing. Now, what I couldn't record is 5.42, right? There's not enough precision in that measuring device to record to 5.42. It's the 4 that's being guessed, not the 2. So I can't go that far. However, if I add precision to it, now I can guess even closer. Okay? So now I know it's for sure 5.3 because I can count 1, 2, 3 places. It's for sure 5.3. Okay? But now I have to make another guess. Well, it's between the 0.3 and the 0.4. So I'm going to say 5.36 or 5.37 or 5.35. It's a guess. You guys have to make that determination. So that's the last significant digit, the last guessed digit. These other two digits, we didn't guess what they were. We know it's at least 5.3 something. Okay? So when I record significant digits, I have to do it all the way to the last guessed digit. So if I'm ever measuring something in the laboratory, like in a graduated cylinder, I'm measuring the volume. If it hits right on the 10 milliliter mark, okay, then I don't say just 10 milliliters. That's not representing all of the precision in the measuring device. If I just say 10 milliliters, then what kind of device does that represent? It represents something with increments like 0. Nope, that's even too much. Let's do it like this. Okay, now I can guess 10. I can't guess 10 on a graduated cylinder that has a lot of precision in it. Okay, I have to say on the graduated cylinder 10.00. If I think it's right on the 10, I have to guess that. It's right on 10. 10.00. Okay, so I have to show or represent the type of device I'm using by the number of digits that I record. Okay, and your scale does that for you. It tells you a whole slew of numbers on your when you weigh something. That's because it's giving you all the precision in the measurement and guessing the last digit. That's why that last digit goes up and down, up and down. It moves. So you just kind of have to grab it where somewhere in there. Okay. All right. So these are some guidelines that you'll follow. We'll go through these, and then I'll tell you how I think that the best way to recognize significant digits is. Okay, so all non-zero digits are significant. Everything that is not a 0 is significant. 7.314 has 4 significant digits. Okay, everything there is significant. The number of significant digits is independent of the position of the decimal. So if it's 7.314, it's 4. If it's 73.14, it's still 4. All non-zero digits are always significant, no matter where the decimal is. Sandwiched zeros, they are significant. Okay, if they're sandwiched between significant digits, they will be significant themselves. So 1, 2, 3, 4, 5. I have 5 significant digits in this number. Okay. Zeros at the end of a number. So this is where it gets a little complicated, because obviously if it's a non-zero digit, we can count how many non-zero digits there are and determine how many significant figures we have. That's easy, right? But it's when it's a 0 that we struggle, because we're asking ourselves, is that 0 significant? Okay? So zeros at the end of a number are significant. Zeros to the left of the first non-zero integer are not significant. Okay? Insignificant if the number does not contain a decimal point. No decimal point, these zeros are insignificant. Decimal point, they have now become significant. Okay? So this has 1, this has 3. This only has 2. Okay? So those are the rules. Okay, so you might not have figured that out very well, how that works, just by what they told you there. Okay, so I want to try to help you understand it a little more clearly. So if I have a number like this one, 4.70, and I write that number in 2 different ways. 4.7, 4.70. Are their values the same? Yes. So why would I write that? Because because this is representing the number of significant digits in the instrument I used. This does not. Or if it is, it means I'm using an instrument less precise than this one. So the reason that that 0 there is on the end is simply to show significant digits. So does this 0 have any value to it? No, it doesn't change the value of the number, right? No value. So this is how I want you to remember it. If the 0 has value, it is not significant. If the 0 has no value, it is significant. The only reason I wrote that 0 that has no value to it is because it is a significant digit. Or else I wouldn't write it, right? I would just leave it off. It doesn't affect my number at all. Okay? Well, look at number 100 here. The number 100. 100. Do those zeros, if I remove them, will they change the value of the number? Absolutely, right? They're going to change the value of the number. So if they have value, then what do we know about these zeros? They are not significant. So there is only one significant digit in this number. Okay? Because those zeros, these zeros, have no value. Sorry. Because they do have value. Because they have value, they are not significant. Okay? So let's try another few. How many significant figures are in this number? 4. These zeros have value. They maintain the value of 136,500. If I remove them, 1,365 is very different, right? So I cannot remove them without changing the value. Therefore, are they significant? No. If they have value, they are not significant. How many significant digits are in that number? Okay. 1, 2, 3, 4. Do these zeros have value? If I take them away, do they change the value of the number? Yeah, right? They do. So, what does that mean about their significance? They are not significant. They are not significant digits because they have value. The reason I write them is not to show precision of the instrument, is to maintain the value of the number. I have to write them. Okay? If I write a 0 that I don't have to write, that's because it is significant. I have to write these. If I don't write them, then that changes the value. And I can't change the value. How many significant digits are in this number? Okay, so are these zeros significant? No. Are these zeros significant? Yes, because if I remove them, do they change the value? No. You mean no, right? No, they don't. Okay? If I remove those, if I put 0.003657 into my calculator or 0.00365700, would my answer be the same? Yes. Because these zeros don't have value to them. They don't change the value of the number. So why did I write them? Because they are significant digits. They show the precision of the instrument I used to collect that data. So that's why I wrote them. Okay? So that's what you need to remember. Does it have value or doesn't it? So let's look at a few examples. How many significant digits are in this first number? 4. 3.4, 3.400. Are those the same numbers? Yes. So why did I write those zeros if I didn't have to? To show significance. So 1, 2, 3, 4. How about in this number? 4. How about in this number? 3. This one's trickier because it has a decimal place. If there was no decimal place, there would only be 1. But because I write that decimal, that makes everything significant. Okay? So that's why I put that decimal there, is to show 3 significant figures. How about in this last number? Okay? Are these first zeros significant? No. Is this one significant? Yes. Is this one significant? Yes. So I have 4 significant digits. Okay, now let's talk about scientific notation. Scientific notation is how we write big numbers or small numbers. And if it's a really big number, we're going to write it in scientific notation because we couldn't even put it on our calculator otherwise. Okay? And you'll run into situations like that. We'll have numbers like that. So we have to understand how we write scientific notation. Okay, so here I have the number 4,300. And I want to put it into scientific notation. So what does it represent? It represents 4.3 times 1,000. Okay? So what I'm going to say here is 4.3. I'm going to put the decimal after the first number. Okay? And you do that for both situations. Big numbers or small numbers, you put the decimal after the first digit. Non-zero digit. Okay? So I put it here after 4. And then I count how many places I moved it. 1, 2, 3. I moved it 3 places, so that means to the third. 4.3 times 10 to the third. Okay? That's the number. Now, how many significant digits are in that number? As it was written before, 4,300. 2. So because there's 2, I have to have 2 significant digits in my scientific notation. You always represent all the significant digits in the scientific notation. So that's why I put 4.3 times 10 to the third instead of 4.30 or 4.300. Okay? I don't need to include these zeros because there's only 2 significant digits. Okay, so here's another example. 6,200. So once again, there's only 2 significant digits. So I put the decimal there, and I move 1, 2, 3 places, and I get 6.2 times 10 to the third. What if you want to express that number with 3 significant figures? Well, then just add that 0. 6.20. Now there are 3 significant digits in this number. Okay? 6.20 times 10 to the third. And that's 3. Now, if it's less than 1, if it's a small number, we have to move the decimal backwards. So I still put it after the first digit, the first non-zero digit, okay, 6.2, and I moved it 1, 2, 3 places. 1, 2, 3, so it goes to the negative 3 in the reverse direction. 6.2 times 10 to the negative 3. Okay, so here's a pretty large number. 1, 2, 3, 4 digits, significant digits in that number, so I have to put all 4 of them into my number. Okay, and I started here and moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13, 14, 15, 16, 17, 24. Okay? So I get to the negative 24. 6.692 times 10 to the negative 24. Okay? So let's do a few of these. I want to put this into scientific notation. So I'm going to say 1.8 times 10 to the negative 4. Okay, I'm going backwards, so in the negative direction. 4 decimal places. Okay, how am I going to write this one? Yep, thank you. 3.004 times 10 1, 2, 3 times 10 to the third. Why did I put 3.004? Why don't I just say 3.0 or just 3? Because they're all significant. All of those digits are significant. I have to include all of them. Okay? So it seems kind of like a waste to write that in scientific notation. Yeah, it is. But if you're going to, you have to include all the digits. Okay? 300 with a decimal. .00 times 10 to the second. 1, 2, right? Times 10 to the second. Okay, last one. 3.04 times 10 to the 1, 2, 3, negative 3. Okay? And that's how I'm going to write that. You have to include all the significant digits in the scientific notation. Okay? So that's important to do. Okay, accuracy and precision. So when we talk about accuracy and precision, we're just talking about how the data relates to either a true variable or number or how it relates to itself. So if we're talking about accuracy, we're saying that there's a true value and your data, how well does it match that true value? So how well do you hit the bullseye is accuracy. Precision is not hitting the bullseye. It doesn't matter if you hit it or not. Precision is simply how well your data relates to itself. So if you're taking measurements and they're all about the same, so you take 5 measurements of the same thing, and they all come out to be pretty close to the same thing, then you have a lot of precision in those measurements. Okay? You're getting the same result again and again and again. But if you have different results and they're all over the place, then you don't have any precision in your measurements. So that's going to be really bad data. So here we can see that you hit the bullseye with lots of precision. So that's precise and accurate. Here you didn't hit the bullseye, but your data is all in the same area. That's just precision, but it's inaccurate. Here you're just all over the place. Okay? You're imprecise and inaccurate. Okay, now, when we're talking about significant figures and you have a number that you're using in a calculation that it was generated or it resulted from counting something, then you might ask yourself, well, how am I going to determine the number of significant digits in that number? So if you have, for example, a set of counted items like a beaker on a shelf, okay? and you're trying to use that number, there's 10 beakers on the shelf, and you want to use that in a calculation, that number 10. Well, how many significant digits do I use for that calculation? The answer is that if it's an exact number, it has an infinite amount of significant digits, and so you simply don't discuss the number, or you don't discuss your answer from that exact number. You'll do it from the other number in your calculation. That's not an exact number. Okay? So, 3.65 times 10, if this is an exact number, when I do this calculation, equals 36.5, and I'm trying to determine how many numbers to carry over. Well, if I was considering that from this being one significant digit, then I would only say, I would say 40, because I would round that 36, I would round the 36 to 40, because I would only report one significant digit. But because this is an exact number, as it came from the result of counting something, then there's infinite numbers of significant digits, so I'll record my answer according to this number, which is 3 significant digits. So I will say 36.5, which is also 3 significant digits, to carry over or maintain the significance of that data set. Okay? So that's what we mean by these exact numbers. Inexact numbers have uncertainty or significant digits. Those exact numbers, a result of counting, don't have any. Okay? Uncertainty. There's no uncertainty in it. Okay, how do we round numbers? So if we're going to round something, we're going to round it according to the number. So if I'm going to round this to 3 significant digits, because I need to record my answer in 3 significant digits, okay? Because if I do a calculation and it gives me a whole bunch of numbers, and I'm saying how many numbers do I keep, all right? Then I go to the 3rd significant digit, and I look at the number that comes after it. And that's going to change this number, or keep it the same. If it's below 5, so 4 or less, then it keeps it the same. If it's 5 or above, it changes it. It increases it by 1. And so then for this number, that's a 9. So that 4 will become a 5, 3.35. And so I round it to 3.35. Okay, so let's round these to 3 significant digits. What's the first one going to be to 3 significant digits? What is it? 61.4. Because I only want 3 digits. 3 significant digits. If I said 0, 0, those zeros are all significant. They would all be significant. Because they don't change the value of the number. So they would be significant. So to 3 significant digits, 61.4. How about the next number? Okay, to 3 significant digits. Good. How about the next one? Okay, these zeros are not significant, right? So I start here. 1, 2, this is the 3rd significant digit. So it becomes 0.0665. Okay? All right, so that's how I'm going to round those. Now, if I am doing a calculation with numbers that have significant digits in them, and it's addition, then the way I'm going to do the addition is I'm going to line them up by decimal place. I perform the calculation, and then I will cut it off, just like they're showing me here, to the number that has the least significant digits after the decimal. Okay? So in this case, that's 37.68. So I cut it off after 2 decimal places, and I round it. So my answer will be 152.83. Okay? Because I'm going to round that 2 up to a 3. 152.83. So let's do that for these. Okay? Now, before I set this up or try to align it by decimal places, I don't need to. Okay? Because you can look and tell me how many decimal places am I going to record in number 1 here? 2, right? Because this has the least number of decimal places. This has 3, this has 2, so I'll cut it off at 2. So when I find my answer, what is it, by the way? 4.26 plus 3.831? 8.09. I'm going to cut it off right there. Okay? To 2 decimal places. How many decimal places am I going to record in this number? Just 1 decimal place. Okay? 8.321 minus 2.4. What is it? Say it again. 5.9. To 1 decimal place. Okay? That's where I'm going to cut it off. All right. So I don't need to actually line them up. I can just count whichever one has the least number of decimal places, and that's how many decimal places I'm going to record. That's for addition or subtraction, which is different than multiplication and division, which let's see. Okay, they want me to go through this first. All right, fine. Scientific notation. Oh, I see. Okay, yeah. So if you're going to do it by scientific notation, you're going to want to convert them to their decimal form so that you can see how many decimal places you need to line them up by. 9.47 times 10 to the negative 6. 9.3 times 10 to the negative 5. Okay? This could be tricky because it's 9.3. Okay? 9.3 has the least. This one has 9.47, has the most decimal places, but it would be hard to see that unless you actually line it up here. Okay? So with the scientific notation, if it's really small like that, a lot of times you might want to actually convert it back so that you can see what it is. Okay? Okay. All right, don't focus on that. Okay, so now for multiplication and division, it's a little easier. Because all I have to do is I have to look at how many significant digits are in every number that I'm using in the calculation, and then ask myself, which one has the least? How many significant digits are here? How many? 2. How many here? 4. 4. So when I report my answer, okay, it needs to be to the one that has the least. This only has 2, right? These have 4. So my answer needs to be to 2 significant digits. So this is what I get on the calculator. Okay, this has the least number, so I'm going to take this 9 and I'm going to round it by 6. So that's going to bump it up a whole number, and then this will all round to 3.0. Okay? So my answer is 3.0. Okay, so now we're going to talk about dimensional analysis and conversions. We've already talked a little bit about it, but we're going to do some more examples. Okay, so these are conversion factors. These are the relationships between two quantities. 1 gallon equals 4 quarts. So my conversion can either be to gallons by using the conversion factor 1 gallon per 4 quarts, or to quarts by using the conversion factor 4 quarts for 1 gallon. Okay? But I don't have to think a lot about which one I'm using, because if I set up the dimensional analysis correctly, it will tell me which one I need. Okay? So here they're saying if we want to convert 12 gallons to quarts, okay, using the 1 gallon equals 4 quart conversion factor, okay, then I start with what I'm given, 12 gallons, and I want to convert that to quarts from the gallons. I have to get rid of my gallons. I'm left with quarts. Now I'm going to get to my quarts. Okay, so I will take 12, and there's 4 quarts in 1 gallon. 12 times 4. That's how I'm going to get there. Okay, 12 times 4, and I get 48 quarts as my desired result. So as long as I have it all set up correctly, it'll be easy to put my numbers in the correct place. I'm going from gallons to quarts. That's what's on top. What goes on top is the process that I'm following. Gallons to quarts. Okay? 360 feet to miles. Here's my conversion factor, 5,280 feet in 1 mile. So, I'm going to start with what I'm given, 360 feet. Okay? I could even look at it like this, 360 feet. I'm going to convert that to, they want me to convert it to miles. Okay? So that's the process. That's what I need to see on top. Feet to miles. From the feet. Okay? There's 1 mile in every 5,280 feet. So the feet cancel. I'm left with miles. This is going to tell me how many miles are in 360 feet. Okay? So 0.068 miles. 0.068 miles. That's what I should get. Convert 0.0047 kilograms to milligrams. So, here's your 2 choices. Remember, or I guess not 2 choices, but these are the different conversions that you're going to need. Okay? We have 1 kilogram is 1,000 grams, and 1,000 milligrams is 1 gram. Okay? So if I want to set this up, I could do it in a couple of different ways, but I could set it up like this, 0.0047 kilograms. And I want to go to first grams, and from the grams I want to go to the milligrams. So that would be a process that I could follow. Okay? Or I could set it up 0.0047 kilograms straight to milligrams from the kilograms, as long as I know what the prefixes mean and I'm using those correctly. Okay? Then I will have it correct. Okay? So there are 10 to the negative 3 kilograms in a gram, and there's 10 to the 3rd milligrams in a gram. So that becomes my conversion. Okay? Or I can just set it up here. Kilograms, 0.00, there's a 1,000 grams in a kilogram, or there's 1,000 milligrams in 1 gram. Okay? So either way, I'm going to get the same answer. All right? Depending on how I set it up. My grams cancel. Here my kilograms cancel. I'm left with milligrams. On the top, I'm left with milligrams. Okay? So here they're doing it obviously in those 2 steps. Kilograms to grams, and then grams to milligrams. And you get 4.7 times 10 to the 3rd milligrams as your answer. Okay? All right. So here's they're saying they're saying alternatively you could have done it in one step, or not one step, but one equation, okay, where you take kilograms to grams to milligrams like I showed you, okay, and you could set that up in that way, as long as you're using everything correctly. And once again, you could just use the 1,000 milligrams to 1 gram here, if that makes more sense to you. If that's making sense to you, then use that. Don't use the 1 milligram to 10 to the negative 3 grams, because maybe you're like, I don't understand that, Mr. Crandall. It doesn't make sense in my head. Okay, then don't use it. Use the 1,000 milligrams to 1 gram. Either way, you're going to get the exact same answer. It doesn't matter which way you do that. Okay, so let's do a few conversions here. 5.5 inches to millimeters. Okay, 5.5 inches. And inches to centimeters, there's a pretty good conversion factor to that. For that, 2.54 centimeters equals 1 inch. So let's first do that one, inches to centimeters. And then I can go from the centimeters to the millimeters. Okay? Whoops, what am I doing? From the centimeters to the millimeters, all right? So my inches go down here. There's 2.54 centimeters and 1 inch. What am I going to put for the conversion between centimeters and millimeters? Relate it to the base unit. How many centimeters are in a meter? There are 100 centimeters. Centi is 100, like a okay, like a centipede. Thank you. Yeah, 100 legs. Okay, or what's a milli? 1,000. Okay. So you can set them up that way. You just relate it to the base unit, and you can set them up that way. All right. So there's 100 centimeters in a meter, and there's 1,000 millimeters in a meter. And I can easily get there. Inches, inches, centimeters, centimeters. And we're out of time. So we'll finish those later.